For the intro.
Yeah, Andrew's not here. Wow.
Please hit the like and subscribe button before watching this video.
Yeah.
Oh, like and subscribe. There we go. There we go. Okay, so let's chit chat about the labs. So there's three distinct parts to this lab. Two of which you have constant velocity, one of which, the last one, you have accelerated motion. Okay? Now remember, the beauty of any physics problem is that it only works, or forces problem, only works out one of two ways. Literally, this is it. You're either at a constant velocity and all the forces are in equilibrium, they add up to equal to zero, you draw it tip to tail, you end up back at the origin, however you want to view the story. Okay? The other side of it is that you have accelerated motion, the forces aren't balanced, you have a net force, and it accelerates. That's it. That's it. Those are the only two games in town. Now, you look at this first set of problems, and you said, okay, here's this block of wood. You had a force applied of, I don't know, 1.10 newtons. Now, here's what you have to understand. What's the only reason I have to keep applying a force to keep this physics book moving?
There's a force in the opposite direction.
There's a frictional force opposing it, okay? There is a frictional force opposing that applied force. There is the frictional mafia. If we lived in a universe without friction, a number of things would be different. You couldn't drive your car because you could never get it to move because there would be no friction between the tires and the pavement. You couldn't even tie your shoes in the morning because you couldn't hold on to the thread. Okay? You go to tie your shoes, it's like, oh, this sucks. I have no friction. Yes?
What would you be able to do?
Absolutely nothing, really. You wouldn't even be able to walk. You could fall, but then you couldn't get back up because there would be no friction to hold.
So you'd just be like,
Yeah, it would be so weird. The universe would
It'd
just
be like trying to do everything on ice, but you couldn't get
yeah, but yeah. So
Is ice like the only frictionless thing?
even ice isn't
It's not-
pure ice is kind of frictionless, but even that has some friction to it.
Oh wow.
Okay, so here's the story. So if you have to apply a force to keep something moving, that means because there's friction. The only time this is really applicable in a real case situation, real world situation, is when you're in deep space. Like let's say, for example, we're talking about the Apollo 11 missions that went to the moon. So they orbited the Earth a couple of times, make sure everything was cool. Then they fired the engines and they coasted to the moon. So the only time that you really have a situation where you do not have to have a force to maintain motion is when you're in deep space and effectively in a zero gravitational field. So if this book, if I was in deep, deep space and I gave this book a push, I would just push it and then it would maintain that velocity. So that's the only situation. Do I have to apply a force to get the book to move? Absolutely. Do I have to keep applying the force to keep it moving? No, because of this concept of inertia. So that's what Galileo did. Galileo had the insight to go, what if we eliminate, and being Italian, he knew about this, what if we eliminated the friction mafia? And he's like, oh, right, hey, that would be cool, right? Then no one would have to have that situation where you would have to keep applying the force. So, I think you've got your F gravitational force and your force normal. Okay, boom. So diagram number one, this is what this should look like. I should see the scale, I should see the labeled forces. Diagram number two, you're going to draw it tip to tail, FG, force normal, force applied, boom, you should end up back in the origin. Use the same scale for both diagrams, okay? When you get to question number three, okay, this is where you're going to find this line of best fit. So on number three, you have your force friction here, you have your force normal here, you're going to have some data points. you're gonna draw that line of best fit. Now, I underlined it. I said circle the points on the graph. This graph, depending upon your data, might not go through 0, 0. Okay? It might not. Depends. So, here's the point. Is that the whole reason that you draw a line of best fit is so that when you find the slope, you're finding it based upon points that are on the line of best fit. Okay? That's why you draw the line. You only pick the points that are on the line. If your data points are on the line, winner, winner, chicken dinner. You can use them. If they're not, you can't use them. And everybody's slope is going to be different because everybody had different surfaces. So the only thing I can grade is your work. Now, you get down to questions 7 and 8. Okay, 7 and 8, hey, this thing's going to accelerate. So on 7 and 8, you know that, both parts of number 7. So you've got force friction equals mu times force normal. Okay? That's the story. So I've given you the value of mu, you have that. So what are you going to do, Thatcher, for your force normal?
Use the friction value.
Yeah, but how are you going to find the frictional value to find on number 7? How are you going to find the force normal?
Is it your mass times your mu?
Nope. Connor asks.
You find the force of gravity with acceleration and mass, and then you do the opposite of that.
Which acceleration?
The acceleration of gravity?
Yeah. So remember, force normal is the same as Fg, which is mass times your gravitational acceleration. You know we're on Earth, gravitational acceleration is 9.8. Don't get hung up on making weight a negative value. Just get the number. Then decide in the context of the problem, does it make sense to make it negative? Well, this is an absolute value, so it does no good to end up with a negative force normal because it's an absolute value anyway. Okay? So this is just going to be mg. You know the mass of the car, you know what g is. Boom, multiply it by mu. Now, in the context of the problem, what's the initial velocity of the car? A positive or negative value? Positive, right? Car's going to come to a stop. What's going to be the sign of your acceleration? Negative. Well, F equals ma. So it's the only way you can generate a negative acceleration is if you have a negative force. Okay? So mathematically, you will never generate a negative force friction. But what you have to do is look at it in the context of the problem and go, hey, does this make sense to make this a negative value? Let me give you a hint on number 8. Every answer on number 8, there's different place values, but every answer on number 8 should start with a 5.
Oh, let's go.
Okay? They're not the same number, obviously. They're vastly different, but every answer should start with a 5. Okay? So if that acceleration on 8 is wrong, everything is going to be wrong. So that acceleration on number 8, for that acceleration should be between 5 and 8 meters per second squared. Okay? Should be between 5 and 8. Now, when you get to number 9, what are the 2 most important words on problem number 9?
How much?
Constant velocity.
Constant velocity. Those are the 2 most important words on problem number 9. Because once you see constant velocity, what do all the forces have to add up to?
No.
Goose eggs. Okay? Simple. You don't have to add up to like negative 500. Okay? It's just 0. That's all you have to worry about. So you look on number 9, you're going to have 4 forces, just like you did with the block. Gravity, normal, force applied, force friction. Make all of the values add up to equal to 0. Your answer to number 9 would make a horrible GPA. Okay?
That's pretty good.
Suboptimal.
If you're on the KU basketball team. Just saying. Okay. That might get you on the honor roll. All right, now let's talk about the equilibrium problem with the force table. So here was the setup, here was the force table, boom. You had the forces being pulled down like this, okay? So, start with this idea. Was the ring accelerating?
It should not be accelerating.
No. So therefore, the system's in equilibrium. So basically, what you're looking at, you have A, B, and C. So, Sydney, what was the value of your force for vector A?
0.42 kilograms and 4.12 newtons.
4.12 newtons?
Alright.
Okay. So here's the story. So what we're going to get into later on is this concept of tension. Okay? Tension just means it's an upward force typically provided by a string, a cable, a wire, or something like that. So if you look at what's happening, and this is this difference between a contact force and a non-contact force, when you get over here to this last question on number 13, where you're talking about a contact force versus a long-range force. And this is also Newton's laws of motion. So if this is her mass and multiplied by g, you got 4.12. So what that means is that the Earth is pulling down with a force of 4.12 newtons. Now, by Newton's third law, and this is kind of going to be Newton's third law day, that means there has to be an upward force of also 4.12 newtons. So everybody gets the idea that the weight is being pulled down by the Earth. And it is. But by Newton's third law, and that isn't Newton's suggestions, okay? It's Newton's laws. If the Earth is pulling down on the mass with a 4.12 Newton force, that means the mass is pulling up on the Earth with a force of 4.12 newtons, okay? And this is what we call long-range force, because of the fact that there's no direct contact between that object that's hanging from the end of the string and Mother Earth, okay? You can move your hand in between. It wouldn't bother, it wouldn't disturb it at all, okay? So that's what we call long-range force. Most of the interactions in life that you have had aren't long-range forces, okay? It isn't like I'm going to sit over here and go, and Sydney goes, hey, Mr. Burkamp, and she drops the pencil and she goes, hey, can you pick up my pencil for me? And it isn't, I wish I could, it isn't like I can do this Jedi thing and put my hand out and then direct my energy force towards the pencil, lift it up, have it levitate, and then swing it over and go, oh, here you go.
That's only possible.
Which would be cool. Don't get me wrong. Okay, that would be cool. I could do parties on the weekends like, oh, Burkamp, do the Jedi trick. Okay? I'd never have to teach them. But we can't do that, okay? But that would be an example of a long-range force. In reality, what would I have to do? Sydney drops her pencil. She goes, Mr. Burkamp, hey, can you do me a favor? Can you help the student out?
You have to touch the pencil.
Yeah, I'd have to reach over, grab a hold of it, pick it up, and hand it to her. Okay? That would be an example of a contact. That's what almost all of your experience has been in life, is contact forces. You hold a pencil and you write. You tie your shoestrings. You grab a carton of milk. Boom. You press down on the gas pedal in your car. Those are contact forces. So, in terms of Newton's third law, that's a set of equal and opposite reactions between the Earth and the weight. There's also a set of equal and opposite forces between the string and the weight. So the string is pulling down, or excuse me, the weight is pulling down on the string is pulling up with an equal and opposite force. So when you see tension, and you're going to, That's just the upward force provided by the string. So if I take this rubber stopper and I hold it up like this, system's in equilibrium. Gravity's pulling down on the stopper, the tension in the string is providing an equal and opposite force, the system doesn't accelerate. Okay? Now I let go of it, I lose the tension, boom, it begins to accelerate. Okay? Got that. So that diagram for the force table should look something like this. You're going to have A, B, C. Typically that's what that diagram is going to look like. Make sure I see the scale, okay? Don't just randomly draw arrows and think, oh, Burkamp will know what the scale is. I'm not. Everybody's is going to be different. Now, with Sydney's numbers as big as her, that 4-something Newton force, she could let 1 centimeter equal a Newton. Okay? Legitimate. She could let 1 centimeter equal a Newton. But if they're generally in that 1 to 2 range, I'd maybe let 2 centimeters equal a Newton, so that way you're not drawing tiny little vectors. Okay. Cool with that one. Now, the most complex one is the one with the cart. Okay? So here's the cart, boom. So here's the story. The first trial, you had a 10-gram mass hanging from the end of the string. Okay? You let go of it. Right away, you began to see an acceleration. So right away, what did the forces not add up to?
0.
0. This is the only one where you have accelerated motion. Okay? It's the only one. So here's what you want to focus on. Once you see acceleration, there has to be a force, because Mother Nature is a lazy prima donna. Mother Nature is not going to go, hey, I'll make you accelerate. No, let's just do that. No, Mother Nature is not going to do that. She's too busy hanging out in the hookah lounge. Mother Nature goes, I am not going to make you accelerate. You want to accelerate? That's on you. You find a way to generate a force. And guess what? The net force is always going to act in the direction of the acceleration. So here's the story. So one of the things that you did over here on page 3 is that you had to calculate the net force. So what we're assuming is there is no friction, there's nothing happening. The only force available to make this system move is gravity pulling down on that 10-gram mass. Now, to find the value of that, 10 grams converted into kilograms multiplied by 9.8, you get 0.098 newtons. Okay? That's the force. That's it. That's the force. Now, I want to look at 2 different scenarios. Scenario number 1, we just cut the string. So in other words, we're holding it like this, boom, we cut the string. Connor A, if I just cut the string, what's the only force acting on it? Gravity. And what's going to be the numeric value of that force? No. It's on it. That's acting on a 10-gram mass. You're making this difficult. To get this 0.098 newtons, we took 10 grams, we converted it into kilograms, we multiplied it by the acceleration due to gravity, which is 9.8 meters per second squared. And we got 0.098 newtons. So visualize this. Here's this 10-gram mass, and gravity is pulling down with the force of 0.098 newtons. I cut the string, Connor. What's the only force acting on it? That's the acceleration that it's going to cause. Don't confuse the acceleration with the force. And what's the numeric value of that force?
0.098.
Beautiful, because it's only 10-gram mass. Okay? So when I cut the string, The only force acting on it is 0.098 newtons. So if you look at F equals ma, oh, I have 0.098 newtons. If I divide it by the mass, then I would work backwards to Connor, and I would get an acceleration of negative 9.8 meters per second squared. Now, here's the next question. And let me explain my rationale on how and the sequence of these questions on this last page. So when you get to question number 5, and it says that the string had just been cut, what's the value of the force acting on the 10-gram mass at that point? That should be 0.098 newtons. Okay? That's it, because that's the only thing acting on it. There's nothing else. There's no squirrels, nothing. It's just 0.098 newtons, which is going to create an acceleration of 9.8 meters per second squared. Okay? Now, when you get to question number 7, and this is one of the great mysteries that physicists had to explain. If I take Gary the golf ball and I drop Gary, I'm going to get an acceleration of 9.8 meters per second squared. I take Hank, much more massive, right? And I drop Hank, I'm going to get the exact same acceleration on Hank as I do on Gary. I'm going, oh, man, this is tough, okay? So here's the point of these questions. Is there more gravitational force acting on Hank?
No. Yes.
Yes, absolutely. You don't believe me? Hold Hank, okay? Hank is heavy. There's a lot of force to hold Hank. There's more gravitational force acting on Hank than there is on Gary. But Hank has more stuff, right? So therefore, Hank has more inertia. So there is more force acting on Hank. True. But also, Hank has more stuff. So you have more force acting on more stuff, you end up with the same acceleration. So let me give you a different way to view those questions 5 through 9. We're going to draw a graph. And we're going to put mass along the x-axis, and we're going to put Fg on the y-axis. Okay, so we have two masses. We have 0.010 kilograms, and we have 0.020 kilograms. Okay? Leave the card out of this for now. Just focus on these. So that 0.10 had a force of 0.098 newtons, and this one had a force of 0.196 newtons. Okay? Cool. Nice linear function like this. Sydney, do you have enough information to calculate the slope of that line?
Yeah.
What would the slope of that line be? How would you find it?
I take the change in y over the change in x.
So you're going to take 0.0196 newtons minus 0, because this thing is going to go through 0, 0, because no force, or no mass, I have no force. And then I'm going to divide that by 0.020 kilograms. So somebody using the magic of your calculator, take 0.196 and divide it by 0.020 kilograms. Let me know what you get.
9.8.
Ooh, we get 9.8 meters per second squared. So here's what solved the mystery. If I double the mass, I go from 0.01 to 0.02. I double the force acting on it. Okay? So force is proportional to mass. The more mass I have, the more force I have. But I end up with the same acceleration. And here's the reason why. Gary has a lot of stuff, which means it's going to take more force to get Gary to move, or excuse me, Hank to move. Let's get Hank back up here. There's Hank. So here's Hank. Hank has a lot of stuff. Gary doesn't. So I have to have more force acting on more stuff to get same acceleration. So this is why when you look at this question, and by the way, all of your questions on number 10 are absolutely false. So here's the heart and soul of this question, and that's part B. It says everything in free fall accelerates at the same rate because the same amount of force acts on everything. This is why I had you do calculations on 5 and 7. If it was the same force acting on everything, there would be no need to calculate anything. What's the force on anything? Pick a number. It's going to be the same for everything. It's not. Okay, it's not. I drop Hank, I drop Gary. The forces acting on them are vastly different. But do we end up with the same acceleration?
Yes.
Yes, because the force is proportional to mass, which is proportional to and creates the same acceleration. Okay? So do not tell me, oh, gravity is the same for everything. No! Stop! Okay? Force of gravity is proportional to mass, which is proportional to inertia. Okay? Do you end up with the same acceleration? Absolutely. But it's not because the same force acts on it. Okay? Cool with that. So yes, everything on number 10 is false. All right, now let's talk about number 11 on that last page. And let's say you get to a problem like this and you go, man, I got nothing. I don't know how to do this problem. But this is why you write stuff down in a lab setting. Okay? So I got a 200 gram mass here, and I got a 600 gram mass here. Okay? So right away, you got the 200 gram mass. Focus on that. Focus on the 200 grams. Is gravity going to be pulling down on that 200 gram mass?
Yes.
Yes. Luke, how am I going to determine the amount of force created by gravity acting on that mass?
I did the 0.2 kilograms
Beautiful.
times the acceleration, or the acceleration of gravity, so 9.8 meters per second squared.
And what did you get?
1.96 meters.
Beautiful. So there's the gravity mafia is pulling down on that with 1.96 newtons. Now, is the gravity mafia pulling down on the 600 grams?
Yes, but then again, it's getting countered by normal force.
So the table, just like Alex said, is providing a force that balances that out. The only thing that's working against this 1.96 newtons is the upward force of the tension because you're dragging the 600 gram mass with it. So here's the most common misconception. Oh, 600 grams, that's an opposing force. It's not. Does it have mass? Yes. Does it resist motion?
No.
Yes, absolutely. But so does the 200 gram mass. The 200 gram mass doesn't want to fall. If you had 200 grams in a zero gravitational field and I let go of it, it would just float right there. So everything resists a change in velocity. The 200 grams and the 600 grams. So here's the story. If you look at F equals ma, which is the heart and soul of this thing, the force acting on the system to make it accelerate is the 1.96 newtons. Okay, that's what you've got. Question being is which mass do you use? Charles, do I use the 200 gram, the 600 grams, or the combined mass?
Combined mass,
Why?
because it's all the mass in the system total
Which is resisting a change in,
motion.
yes, okay? It isn't just the 200 gram that's moving. It isn't just the 600 gram that's moving, okay? Everything wants to remain at rest. We just happen to have a string attaching the two systems together, okay? So the only way you would ever use just the 200 gram mass is if you just cut the string, okay? So do not view the 600 grams as an opposing force. Where we take that into account is when we divide by the total mass of the system. That's where that's taken into account. So your answer to number 11 would make an GPA at best. Okay, an GPA. All right. Anything else?
Question time?
Question time. It's question time. Yes.
Number 12.
Yeah.
What specifically do you want on that?
Well, here's the story. Something where something is providing a force and something is providing an opposite force. So let's start with something simple. Is gravity pulling down on the block?
Yes.
So what's the block doing?
It's going to accelerate.
No.
The-
No, you're talking like an action reaction. Is the table pushing down on the block because of gravity?
It's pushing up on the block.
Okay, hold on. Gravity's pulling down on the block, right? So gravity is pulling down on the block. So what's the table doing?
Pushing up on the block.
There you go. There's an action reaction. Okay, so you could say table's being pulled down by gravity, the table is pushing back up on the block. That's one of them. You could use the string. You could use gravity pulling down on the suspended mass. There's any number of things. Okay? Charles, do you have a question?
I do. 6 on the front, the very, very front. About the playing basketball in cotton socks.
Dang, Charles.
Okay. All right, that's cool. So let's just put, I'm guessing you spent some time on the court.
Yeah, a little
Okay.
bit.
A little bit. So, here's you, okay? And you have on normal sneakers, okay? I'm gonna try and guard you. And I am in cotton socks. Who's gonna have the advantage?
Me,
Why?
'cause you are gonna slip.
Don't
and
say
slide.
that, oh, it's because you're old. That's not the reason.
No.
You don't have as good friction? Is that what it is?
Part of it. What's gonna get you the advantage?
Being to accelerate?
Be able to accelerate. F equals ma. So if you're gonna have a bigger acceleration, what's that gonna require?
What force?
What's creating the force?
You running?
Rhymes with friction.
Friction.
Okay? You have an advantage because when you try to accelerate, there's more friction. If there's more friction between your shoes and the floor, you can accelerate more. I'm on cotton socks. Okay? I try and push off, what's going to happen?
He starts smoking.
I'm not going to have as much frictional force, right? So if I don't have as much frictional force, what's going to happen to my acceleration? You're making this difficult.
No, you're not gonna be able to accelerate.
Yeah. So the slope of your velocity time graph going from 0 to Chuck might be this. The slope of my velocity time graph going from 0 to Chuck is going to be like this. I can get up to your speed, but it's going to take me longer. Okay? Because I don't have as much frictional force. Does that answer your question?
Yeah.
You seem hesitant. Chuck, stand up. Okay? I want you to assume the defensive position. Break down, hit. Okay? Right? I want you to move that. I want you to move to Chuck. I want you to move to your left.
What would Lawler say?
Okay? Now, what's allowing you to do that, Chuck?
Friction?
Friction. What if you were wearing frictionless shoes and you tried to do that?
I couldn't move.
You couldn't move. So what if you had just a tiny little bit of friction? Would you be able to move quickly?
No?
Because you don't have as much force to create as much acceleration.
Well, it would be disappointed in that stance.
Okay?
Okay,
Does that make more sense?
yeah.
Okay.
I think so.
Or if we're running, let's say we're both running at the same speed, you'll be able to stop sooner than I am. Why?
Okay, so I think that's where I was kind of like getting confused.
Yeah.
I was thinking the opposite way.
Yeah, it does. It would play out the same way. If we're both running, you can stop sooner than I can.
But couldn't you get up to speed quicker?
No,
But like, because there's no
okay,
friction.
Chuck, imagine this. We're both driving big trucks. I have a small gas-powered motor from a lawnmower in my engine. You have a big V8. Same truck. Who's going to accelerate faster?
The V8
Why?
is more powerful.
There's more force. Okay? That's equivalent to rubber shoes on a basketball court. There's more force available to make you accelerate. Which means your velocity time graphs are always going to be steeper.
Okay,
Makes sense.
yeah.
Okay, anything else? Going once, going twice. Mr. Ha ha!
The three ways to determine the friction force.
What'd you do in the very first part of the lab? How did you find the force friction? What did you do? Let me give you a hint. You took a yellow box and you pulled it, right?
Yeah.
Okay? That's the first way. Force applied balances out the force friction. Look on question number 7. How did you find that force friction?
Force G equals mg.
Multiplied by? How'd you find your force friction on problem number 8?
Honestly, don't know. Because I have it down on number 1 already. F equals ma.
That's your third way.
Okay.
First way is you pull it. The second one you use mu. The third one you use F equals ma. I'm kind of digging the Snoop Dogg look.
Yeah.
Yeah. Okay. All right. Any other questions? Going once, go. No! What?
Hey, watch it.
So, what's the difference on 13? What do you mean when you say contact force and long range force? Because I didn't think there was any contact going on.
Okay, I dropped this. Is there any contact between this rubber stopper and the earth to make it accelerate?
No.
That would be a long-range force. Gravity is the quintessential long-range force.
Okay, so what would the contact force be? But we didn't do that.
Did you tie a string to the cart?
Yeah?
Was the string in contact with the cart?
Oh, okay, I get it now.
Thank you.
You're welcome.
I think you're good now. I don't think I got
Pastor, so help me God. In the name of physics, bad things are going to happen. Anything else? Going once, twice, so. Okay. Staple that graph to the back. Get that handed in.
I'm going to ask
No.
a question.
No.
Or Maddie.
As long as you've got them numbered and I know what they are.
What are you dragging me into, Connor?
So it doesn't matter if I was to basically flip the zero direction 90 degrees.
What do you
I mean,
mean?
you can ask
As
me
in,
yes. Well, look.
Zero is a positive x-axis. 90, 180, 270. That's it. That's it. There's no flipping to it. Every time. That's how we're defining this.
I guess I gotta redo my graph.
I tried to get away with using like.
Yes. Well, no. That is what causes the gravitational force.
Thank you, brother.
Yeah. Well, we don't have a final, so I guess we do have a final.
You know all the less than y'all.
So
Oh my Chuck. Wait, bro, weren't you in my class with Tay?
Yeah.
Yeah, I remember that. Actually, never mind.
So you did D equals one?
I knew it. I knew it was
I don't wanna do it. Here. Yeah, I think I'd rather.
Okay, so we're gonna do some demonstrations involving Newton's 3 laws of motion. Okay? So,
Was I supposed to?
one of them we're gonna do, and we'll start simple, and we're going to work our way up. That's gonna be the culminating one, okay? Actually, let's get that out of the way, so that way, no, we'll save that at the ending, so in case I get, hurt, you all will have the lesson done. So, let's say that I want to figure out how much force that this fan cart can exert as this, I'm gonna turn this on and let go of it, it clearly begins to accelerate. So I want to figure out how much force is exerted by that fan on a spinning cart. So what am I going to use? Perhaps F equals ma? There's a radical concept.
Yeah, that's crazy.
Like that one.
Yeah.
So how can I determine the mass of said cart?
Wait.
Weigh it. I happen to have a Newton scale. Easy this. So I take this, I hang it up, and I get 4.26 newtons. Okay? So, Thatcher.
Yep.
The fan cart weighs 4.26 newtons.
Yep.
How can I find the mass of the cart?
Divide by acceleration of gravity.
Which is?
1.8 meters per second.
So could I write mass as Fg over g? Is Fg over g equivalent to mass?
Yes, sir.
Absolutely. Okay? So I'm going to come in here and I'm going to write that as 4.26 newtons divided by 9.8 meters per second squared. Cool. Now, let's talk about acceleration. Acceleration is tough to measure. Okay? Mass is simple, distance is simple, time is simple. Acceleration is tough to measure because, by definition, what happens when you accelerate?
You get that.
What's changing?
Change your velocity.
Changing your velocity, right? And not only because you can't measure velocity directly because that's changing, because you can't take distance and divide it by time to get your velocity, because it's speeding up and slowing down, it's awkward, okay? But what are some things that I could measure when that cart begins to move?
Distance.
I could measure a distance.
Time.
I could measure time.
Initial and final velocity.
Well, if we're clever, and we are,
Initial.
what are we going to let the initial velocity equal? Zero. Okay? V naught's going to equal 0. Cool. So what equation relates velocity, initial, time, distance, and acceleration?
That.
No,
Never mind.
we have time.
Oh, yeah. E equals 1/2 h squared plus v naught t.
So Thatcher says 1/2 AT squared plus V naught time. We're clever, and want to let the car start from rest. This is what you all did yesterday on the lab. V naught's going to equal,
Zero.
this goes away, Snoop. I need that equation solved for acceleration. What do you got?
I have 2 airbags. Screw it all, right?
is it 2x? Are we solving for acceleration?
Yes.
Oh, okay. So it is 2x, and then over t, and then don't you like square root, right?
Oh, no, just keep the square.
You keep the square.
Equals A, right? Cool with that. So, let's do a simple experiment. So, I need you to time this. For those of you that are watching on YouTube, we're just gonna let this thing roll a meter. You'll miss out, but we'll get you the data. Okay,
Smash that subscribe button.
all right, so we're gonna go 3, 2, 1. Yeah.
It's like, there's stuff on it.
No, she watches
No, you're good.
And hit that like button.
Yes.
Let's get Bridger into 2 mil.
Okay, so we're up to speed. Ready?
Yep.
3, 2, 1, go. Stop. What'd you get?
2.9 seconds.
2.9 exactly?
Yeah.
Okay,
Okay, play.
so we got a time of 2.90 seconds. We traveled exactly 1 meter. So then we can calculate the acceleration. So we got 2 times 1 meter, somebody do the math, and divide that by 2.90 seconds squared.
2.3 or 2.4 or 0.24. Sorry.
Oh yeah, there's a big difference. 0. Point what?
2.4.
Exactly?
It's 2.378. But
So 2.378. Oh, close enough. We'll call it 0.24. How now? There's my acceleration. So somebody take 4.26 and divide that by 9.8. 4.26 divided by 9.8.
0.435.
0.435 kilograms times 0.24 meters per second squared gets me what?
1.04. 0.104.
0.104? Newtons. So what that means is that when I turn on this cart, okay, I turn this on, let go of it, that's going to be the force provided by the fan to make this thing move. So here's the story. This thing weighs